Less than a week ago, Microsoft announced they created a new kind of thing called a topological qubit for quantum computers. Okay, so what the hell does that even mean? All right, look, there are these things called quantum computers. They're super fancy. That's actually going to be the topic of this conversation. And the claim is for Microsoft that there's this technological innovation that allows them to massively leap forward in making reliable quantum computers. I actually had a conversation with a guy named Brian Lenahan about a year ago, a little bit more than a year ago, where we talked about this stuff because he is the founder of something called the Quantum Strategy Institute. And I asked Brian to explain to me what the hell is a quantum computer, just in simple terms. And he's probably the best person I've ever spoken to on this topic who can just lay out clearly not merely how quantum computers work, which is what most people tend to focus on. They talk about qubits versus bits and stuff like that. But if you like, at a conceptual level, how are they operating? And more importantly, what can they do that non-quantum computers can't do? What can a quantum computer do that a laptop can't do, or even our best supercomputers can't do? What makes them so fundamentally different? And therefore, what kinds of giant opportunities and perhaps risks do they present? There's some really interesting risks, by the way. It pours gasoline on some of the AI risks, but also there are really interesting security risks, cybersecurity risks that maybe doesn't sound so interesting to you. I don't know if you're into cybersecurity. It's not my thing, actually, but there's really interesting things to say about how quantum computers threaten the vast majority of encryption on the internet, 99%, something like that. So it's pretty crazy stuff. I'm not going to, in this episode, talk about Microsoft and the topological qubit, whether it's plausible. Actually, the jury's still out, so Microsoft reported this, but there hasn't been independent verification of their claims yet, so people are a little bit skeptical. It doesn't matter because what really matters is there's lots of research being done on quantum computers. They are fascinating, and I think a lot of people run away from the topic because they're just intimidated by, let me get this straight. I have to understand how computers operate, and then I have to understand something about quantum physics, and then I have to apply an understanding of quantum physics to how it's too much. But this conversation is going to clear it up for you, I think. It certainly cleared up a lot for me. And so I hope you enjoy it. My name, by the way, Reed Blackman. This is Ethical Machines. If you have any questions or comments, please email me at em@reedblackman.com. Also, I've been doing a lot of writing on Substack lately, so please visit reedblackman.substack.com. Subscribe. Most everything on that Substack is free. And yeah, I think you'll like it. All right, let's go talk to Brian. Okay, Brian, the big question: what in God's name is a quantum computer in a way that me, a non-computer scientist and a non-quantum physicist, can actually wrap my head around?
If you think about it this way, there's a big difference between classical computers and even supercomputers and quantum computers. And it's this: if you try to solve a problem, let's say a maze with a classical computer, it takes a linear approach. It starts to go, let's say, a mouse through the maze one at a time. It returns back to its origin and then goes down the next path. But if you've got a quantum computer, you're looking every single potential path at the same time. So this is a massive increase in the potential computational potential that companies can have.
So that's interesting. I was going to ask you a question like, and I know what the answer is, but I wanted to set it up with something like, so we're just talking about super fast computers, right? But
That's that,
you've already pointed to a difference, I take it, because you didn't say it'd be a super fast computer or increasing the volume on the speed of our computers means that mouse would go down each pathway sequentially just a whole lot faster. Pointing out is that it's not just that mouse going through each path faster, it's whatever the hell this means, it's slowing down all those paths simultaneously. And so you get to a quicker result, not because you've done the normal things faster, the thing that a regular computer does, the thing that our laptops do,
yeah,
but it's doing a different kind of thing to get to the answer.
exactly right. And it's what it's doing. So you characterized it well. What it's doing is using properties of nature that have been discovered 100 years ago. Only now in the last decade have we been able to take that information that Einstein and Feynman and all these other great scientists started discovering back in the 1900s to say things like quantum entanglement. And I would never start a conversation off with the CEO with this topic.
Yeah.
But
Oh, yeah.
basically,
Most anyone. Yeah.
The idea here is you've got a pair of socks, a left and a right sock, that quantum entanglement says these two electrons or photons or pieces of nature are innately connected because no matter where that right sock is in the universe, it's connected to the left sock. And so using those properties, we're able to faster results, store more information. And it's not simply a matter of classical zeros and ones. It's matter of all states in between. And so all of a sudden we exponentially increase the opportunities we could do for computation.
All right, so I do want to dive a little bit more into the physics of it all, but before we do get deeper into that conversation, so you said we can do the kinds of calculations that we can't do with today's best supercomputers. That it would take today's supercomputers years, hundreds, thousands, tens of thousands of years to do it. They're just doing that one by one route through the maze, even if it's really fast. The mazes are so
Yep.
complex that it's going to take thousands of years. So it's the nature of the quantum computers that it can do calculations in a different way, allowing it to solve problems we can't solve now. So just give me some examples of some of those problems that we can solve using a quantum computer, at least in principle, that
Yeah.
we can't do with a supercomputer.
Yeah, let me give it in sort of levels. So there are near-term uses of quantum computers that we're already seeing in use today. There are ways to connect up your quantum and classical computer, and then there are pure quantum computer applications, which are years away. That's quite often read the first question I get asked is when quantum.
Yep.
When quantum is not a year, it's a range. If you think about things like portfolio optimization, you're a bank, you've got trillions of bits of data. When you try to run an optimization routine that tries to characterize a portfolio as close to reality as you possibly can, you can only make assumptions because you can't actually use today's classical computers or supercomputers to emulate reality. There's just too
Mm.
many pieces of data. When you start using quantum capabilities, you start approximating much closer that reality. And you're also able to do those calculations in real time as opposed to waiting a day or a week or whatever. So if you're a financial organization and you see that potential, you're going to start pursuing it. And we've already seen JP Morgan Chase, CaixaBank in Spain, all of these larger entities start to use portfolio optimization via quantum techniques. So that's
Okay.
one example.
Okay. So it's something like this. Look, you want to make certain kinds of predictions about how the future is going to unfold so that you can invest your money properly, invest your money well, something along those lines, right?
Yep,
And in order to make the best predictions, you're going to have some model of what the world looks like. You have to have some concept of what the world looks like in order to predict how it's going to continue to unfold. But the world's phenomenally complex. There's a tremendous amount of variables. There's countless causal relations among all those variables. And you just can't model it very well with today's computers because they don't have the power to do it. But
exactly.
quantum computers can countenance all those variables. It can just handle more data, which means that it can get, at least in principle, a better mirror or duplicate of reality. One might say a digital twin of the reality that you're looking to model.
Exactly. Or a
And
quantum twin.
quantum, yes, okay, great. Quantum digital twin, wonderful. And so if you could model the world, if you could paint a digital picture of the world, finer grain detail, a fine tipped brush as opposed to a broad brush, then in principle, you should be able to make better predictions. And
Exactly
that's
right.
the kind
More
of thing that we can
accurate.
do with a computer.
That's exactly right. And that's just one example. Another example is something called quantum sensing or imaging. And that field is actually even more advanced than quantum computing is today. So imagine if you were an oil and gas company and you wanted to optimize your spend in terms of how do you go out and find where the most likely candidate wells are. And there are much greater accuracy levels in gradiometers, those things that actually look into the earth to sense for oil and gas pockets. And so let's just say it's not oil and gas what you're looking for. Let's say it's treasure. You're an archaeologist and you're looking for something that's what's in this general area.
Mhm.
Problem is today you've got to dig pits in order to see if you can find the actual ashes of human bones or treasure or
Yeah.
whatever. The University of Birmingham has come up with something called the quantum gravity gradiometer that allows you to look more deeply into the earth. and more quickly find those important caches without disturbing the earth anywhere near as much.
Yeah, I don't understand this. I've read about it. So the example that I read about had something to do being able to use quantum computers to do this kind of detection that you're talking about, detecting quantum particles at a distance without a causal interaction between those things. And the example that they were using was a submarine. So
Mm.
the military can use it to sense submarines out there far away in the ocean without bouncing some radar-ish thing off the submarine, thus alerting them to their surveillance. But
Imagine
one
this is
question is I barely understand. One, I don't understand the physics behind it. But two, I'm also a little bit murky about the is that an application of a quantum computer? I don't think of my laptop as sensing things. It's processing. And when we talked about quantum computers processing variables, millions, billions, whatever variables, there's no sensing there. So what's the connect between this ability to use quantum computers and quantum sensing bones, oil, submarines, etc.?
Think about it this way. There's two separate tools that you're using. Imaging capabilities, imaging hardware that allows you to look out or look down. And I'll describe that in a second. But then the quantum computer, which is doing the analysis part. So you're gathering the data through one tool and you're analyzing it through the other. So that's really the marriage of quantum sensing and imaging and computing. So let me talk a little bit
Yeah.
about why quantum sensing can be more accurate. If you think about the early days of radar back in 1935, when the Brits were actually looking at how they could see planes before they actually arrived shores, and they came up with the most rudimentary capabilities for radar. And essentially what they were doing was bouncing signals off the ionosphere to actually find those planes. But that wasn't the first attempt they tried. So they were continuously improving. And by 1940, they had a full network of radar systems. But basically, what it does is it pushes out a whole series of signals. The challenge is you have interference from heat, from movement, from other targets. So you don't really know what the target is. You just know that it's approaching. And so by using quantum sensing and imaging techniques that are connected with nature, you're able to see through many of those barriers that you otherwise would not be able to, whether it's in a submarine, in an airplane, or something else.
So so let me make sure I have this right. The general sensing equipment, to put it really dumbed down metaphorical, sort of shoots a thing it's like shooting something at the target. And on that trip on the way over there, it can run into a bunch of things and be interfered with in a variety of ways.
Absolutely.
And the way that quantum physics works, or the way that particles act at the quantum level, is that somehow you've got two things, A and B, that are entangled, meaning that altering one alters the other, or something along those lines.
Yes.
And it does it even though there's no thing that's, as it were, shooting between the two of them. And so that's why we get this sort of spooky action at a distance thing.
Exactly right. Now, the depth to which you and I are going in this conversation is
Yeah.
much deeper than most any conversation I have
Good.
with business leaders and so on. So it's fascinating, particularly for me. One last example of that is cars that have massive sensing capabilities are on the streets. We already see them, whether it's Tesla or some other model that has lots of sensors. One of the challenges is they can't see around a corner. Believe it or not, quantum imaging techniques are now starting to help with that problem. A problem that a traditional computer couldn't handle, we start to see some benefits coming in other fields.
So that's very cool, obviously, because one of the big issues, as you said, is it can't see around the corner, it can't see tons of stuff, but it wouldn't have to see it because if it's quantum powered or quantum
Yep.
enabled or whatever you want to call it, it would sense things in this quantum way. Okay. So you've got these quantum sensors that are connected to quantum computers. The quantum sensors collect the data, the quantum computers analyze the data, process the data, whatever you want to call it.
Correct.
So you might have a quantum sensor that is hooked up to, I don't know, particles in cars in a 1 mile radius or whatever it is. And then you've got the quantum computer processing, making a digital map of all those cars that can handle all those data points.
Yep. And don't forget about the third tool, which is your classical computer systems. You have all these large companies, medium-sized companies that have spent millions of dollars on their infrastructure. to have a digital transformation or a digital infrastructure in their business. That doesn't go away. These quantum solutions that you and I are talking about are add-ons to that capability so that they become sort of hybrid, where the data gets transferred into a digital environment when it's better to actually process it there. And so the data will move back and forth between these systems to wherever it's optimized. Sometimes you just don't need that capability.
Yes. So when I picture quantum computers, I know are phenomenally difficult to create. Right. Some of them, or is it all of them, need to be held at near absolute zero temperature. So we're talking about colder than
Yeah.
outer space. So when we talk about self-driving cars being powered by quantum, we can't mean, do we? Little mini
Not
quantum
at all.
computers. Okay, so you've got these quantum computers in these insane research facilities that can hold quantum bits, qubits. We haven't talked about that yet, but qubits at
Yeah.
near zero temperature. And then what? You just have something like 6G, 7G. And so the processing is happening off site. So your car is talking to. Do you have a quantum sensor on your car, or is it that there's some floaty satellite quantum sensor that's sensing all the cars that feeds it to your car? Or
These are great questions. These are fantastic. Yeah.
I mean, so what are all the parts here? How does all this connect up? Because it seems there's so many moving parts, and the interoperability seems like a massive headache. And then just the actual speed, just if the quantum computer is doing all this stuff so quickly, but then it has to travel over my Tesla crappy internet, that's going to be a problem.
So here we go. This is great because if you think about a quantum computer, you and I are not going to have a quantum computer on our desk or in our car anytime soon. The next part is I had the wonderful opportunity a couple of weeks ago to actually go visit a quantum lab and
Cool.
touch those physical quantum computers. And these were the kind that you're talking about, where it's refrigerator sized, where you bring the chip down to this just above absolute zero temperature in order to be able to control these qubits, these elements, and be able to move them around and do calculations. So that's one form. But there are at least, if you remember VHS and beta as an example,
Sure.
both of them operated, but we eventually migrated to a VHS solution in the tape days. So similarly with quantum, there are 10 different types, at least 10 different types of quantum technology, and they're all vying for primacy. Which one's going to actually be the final version of quantum technology if we only have one? The one you talked about is something called superconducting. So conducting it down to a very cold level so you can actually control them. There are also photonic qubits based on light and using lasers in control. There are also room temperature qubits, which are based on things like diamond. There's an effort towards miniaturizing quantum computers. So we're really at a stage here when we're actually talking about doing this podcast, a very early stage in the development of quantum computers.
So that's fascinating. I'm interested to hear a little bit more about that arms race. I know. So maybe we should talk a little bit about qubits, how many qubits you need,
Yep.
and how that relates to the issue about noise in the system, having noise resistant quantum. So why don't you tell us a little bit about what it means for why there's such a problem now with noise, what that amounts to in quantum computers? I think the answer to the noise problem is more qubits. And that looks like IBM recently reported that they have something like 456 qubits.
433. Yep.
433. So is it a qubit race? Where do we stand in this race?
Yeah, it really is. It is a qubit race. And here's the reason why, because you're using different elements of nature, whether it's electrons or ions or photons, they react differently. And so you have to control them differently. If you think about the noise aspect you're talking about, noise can come in a number of different ways. We've solved for it in the digital world, but not so much in the quantum world, where it could be thermal noise. So the temperature that an electron is impacted by, or it can be radiation, or it could be movement. There could be a number of different things. So for example, when they're creating these kinds of refrigerator computers, they have to solve for all of those things to make sure that they have the optimal scenario for using it. Now,
So it's just, we're talking about just literally the physical environment impacting the hardware in such a way that it can't do the calculations well.
Exactly. We need to get to the point where you can take your laptop anywhere in the world. It can be cold, it can be hot, but it's
Right.
based on transistors and integrated chips and operates in all those environments. So we're not there yet with quantum capabilities. That's not necessarily a bad thing. What are the types you can have? And they all have different pros and cons, which is a fascinating place to be. Some scale up much better than others. Some have a much higher cost impact.
Mm.
Some are not as fast in terms of their processing speeds. And for the people who are listening to your podcast, they don't necessarily have to sift through all of those things because basically what a quantum computer does today is operate through the cloud. So if you're using a quantum computer, you may not even know you're using it because the interface, the Amazon bracket or Soft Azure or the platform you're using may be simply using it in the background to optimize your output.
So back in the day, I ran operations for a wholesaling company. We had deliveries. And so I used routing software to route the trucks. And for all I know, it definitely was not, but one could be using some routing software one day. It's powered by quantum computing and you just don't know it. You just know that, oh wow, these routes are really good.
Exactly. And companies like FedEx and UPS are exploring the traffic optimization and logistics optimization of quantum computers because gave that maze example. But being able to come up with, when you were in the wholesale business, really getting all of the best possible routes and
Mhm.
prioritizing them, ending them to you, as opposed to this is a 50% probability or 70% probability of correctness. And you take from experience and you continue to provide more inputs. Really, there's the advantage that a number of these transportation and logistics companies are leveraging. And actually, over and above, I guess, aside of financial services, transportation and logistics is one of the leading users of
Mm.
quantum technology.
Okay, so we've got this noise from the physical environment impacting computers, quantum computers in various ways. One obvious way to try to solve for this is to shut down the environment as much as you can. So it's basically
Yes.
it's a highly contained research lab. It's not Bob is going to suddenly come on the door and when draft comes in, everything breaks down. So it's going to be
Yeah.
highly controlled. But even that, there's only so much you can do because
Yeah.
there's quantum stuff going on that you can't close the quantum door, so to speak. And so I take it that one answer is more qubits. So we need more. What qubits are just quantum bits instead of
That's
being
right.
0 or 1. They're 0 and 1 or something along those lines. And the more bits you've got, the more resistant the computer is to interference.
Here's a situation with today's world. So you referenced IBM. They have a superconducting technology that they use, and their roadmap says they've been increasing their qubit counts. So this year they announced a 433 qubit quantum computer. Now, what does that mean? It's all really about fidelity or accuracy. So each one of these computing companies tries to get to a point, despite the noise, of 99, they call it by nines. So 99.9, and then whatever the next digit is, because pretty much all quantum computers today have that capability of 99.9%. But
Percent
really, if
accuracy?
accuracy, but
Okay.
you may think that's a high number, but it's not,
Hmm.
particularly when you're dealing with trillions of bits of data. If you have errors on that last digit, then that becomes a real challenge in terms of the out.
Is it really
So
trillions? That's trillions of
trillions of
data
bits,
points?
absolutely. And that number, if you've probably heard or used this example, there's been more data created in the last 2 years than in all of history. And so that continues. And, that sort of exponential rise in data. So what the technology does is it allows you to incorporate more. So you try to do just that. Now, there are other technologies that have tens of qubits, but they don't require the same sort of freezing mechanisms or worries about impacts of movement and so
Hmm.
on. And so you think, okay, that's great. Maybe we'll try that, but it needs to be able to scale up in order to become consumer friendly. It's a very interesting time to be at. If you listen to a lot of the experts, they'll say, Brian, we need 10,000 logical qubits and 1 million physical qubits. What does that mean? What it means is physical qubits are those ones that you described. So just individual elements that are paired. But logical qubits are and what they do is they help disperse the noise. so that you have these
Ah.
10,000 logical qubits that are actually doing the hard work. And
What's a logical qubit? I know the qubit is just a physical, it's a thing that you put onto a like a board, right?
yep,
Is a
yep.
logical qubit a thing you put on, is it a physical thing or is it a metaphor?
So these are ions that are actually moving through a circuit board, just like you have with integrated circuits today and electricity and so on. These are
Yep.
actually moving through gates on a
Hmm.
circuit board. And
Yep.
there could be 5,000 gates on a circuit board, for example.
Okay.
But it's the physical qubits that are moving around that chip that protect those logical qubits that are actually doing all of the hard work and doing the
Mm.
calculation.
Okay.
So you look at those two numbers, 10,000 and a million. We are so far away from that level of quantum computing that you say to yourself, okay, Brian, so should I just wait for that to happen? And
Mm.
I don't want to jump us too far forward. That's where we are today.
Okay. Okay. I'm not even sure where to start. I have so many questions. So it sounds though that we have enough qubits and logical bits to do some things like routing.
Yep.
Some what I would consider maybe not financially, but at least sort of society wise impact, low risk kinds of things.
I can
If
give you
they,
an example if you'd like.
sure.
Last year at the Port of Los Angeles, there were some major supply chain issues. And so they were using their classical computers to try to come up with new scenarios. Imagine trucks were waiting for hours, containers were being left in the wrong places or not being moved by the actual cranes very well. So what they did was they worked with a company in Canada called D-Wave as well as a local Dix consultant. And they said, okay, here's what we're going to do. We're going to compare the output from our classical computers responses to one that we're going to do with a quantum computer. And really what they did was they took algorithms that were based on quantum technology and used them with both quantum computers and classical computers. Well, what they came up with was a 30% improvement in the overall movement of the cranes, the wait times, and the personnel rosters. So all of a sudden, you had a much more efficient Port of Los Angeles based on this one exercise. And there's tangible results. But this isn't a perfect quantum computer that's sitting on the desk of the people of the Port of Los Angeles. This is all data that's being flown through the cloud, analyzed, and brought back.
One day we're going to want quantum computers to do things like quantum sensing of cars. If we want self-driving cars, or even if we don't want self-driving, one thing that we haven't talked about, but I take it is in the area is precision medicine at the individualized level. So we gather a tremendous amount of data about a given individual. We create their digital twin. We can do that with quantum computers because it can handle all the data points. And then we virtually test out what happens if we introduce this medicine into their system and we see how it goes.
Exactly.
It's stake stuff. We need, though, 10,000 and 1,000,000, whatever those numbers are. How far are we from that? Are we talking like, you said it's in the future? Are we talking 5 years, 10 years, 50 years? Can we even make a defensible estimate on that?
Yeah, so let's do it in a couple of ways. Today, companies are already using something called quantum inspired technology. So they've created the algorithms, the software, but there isn't a quantum computer to run it on. So what they do is take that learning and apply it to a classical computer. So whether that's a magnetic resonance imaging machine
Hmm.
or some other imaging technology that exists today, and they use that same sort of concept in a classical environment. So they're actually
Hmm.
getting some decent results out of this, increasing accuracy. It's a far cry from the potential that we'll have once we have both the quantum algorithms and the quantum computer hardware. And so one of the things I'm going to be speaking at a conference in a couple of weeks, and one of the moonshots that we're going to be talking about is curing cancer. Some of the challenges with cancer is really digging deep down at the cellular level to understand the causes of that disease and how those causes start to spread and emanate. And if we can get down to the beyond the molecular level to the atomic level and really understand what's going on at that level, because we have much more accurate imaging capabilities, whether that is the earliest estimates I've heard of that is maybe 3 to 5 years away. That's really not that far
Oh,
if you
wow.
think about
That's nothing. That's amazing. 3 to
it,
5
right?
years?
Yeah. So if you
Even if
can
they're wrong by double, right? 10 years isn't so
exactly.
bad.
Exactly. So if you can actually have even the beginnings of the sense of understanding of what exactly is happening, let alone trying to cure it, then we can have our experts have a much greater chance of helping people from a societal level.
So one thing that we haven't talked about yet that touches on this kind of issue is we're talking about high stakes situations. Cancer treatment, it is high stakes, although they're also going downhill. It might be a last resort, but if it's not a last resort, but there's going to be lots of applications where maybe not quite life is at stake, maybe life is at stake, but it's high stakes, and where you rely on the predictions of, or we're asked to rely on the predictions of a quantum computer. We
Yeah.
already have issues about reliable and trustworthy, or whatever you want to call it, AI, because of the explainability issue with the black box. Why is it a black box? Because AI is recognizing these really complex mathematical patterns that we can't grasp. You talk about quantum computers and the kinds of modeling they're doing, the predictions they're making. Talk about a black box. I don't care what kind of technique you have to try to understand what's
Yeah.
going on inside the black box, the quantum model, or whatever you want to call it. But um, it's going to be a massive oversimplification of what's actually going on. So
Yeah. If there's
how do we think about explainability, trust in quantum computers? Is it just a matter of if it gives some output, let's try it out, see if it works. If not, don't trust it. What's the play here?
Yeah, so definitely not a blind trust situation. Just like you said, it's really a black box on top of a black box in a
Yeah.
sense where the person who, let's say, is making a decision to invest in both quantum and AI may not know anything about those two topics.
Yeah.
And so when you think about trust, really what is happening today is not so much accepting the output of these quantum algorithms or quantum inspired activities. It's a comparison. We're constantly comparing what the output is from a quantum capability perspective to a classical computer. So you're not doing them independently, at least not the best practice.
Yeah.
And so if you trust your digital capabilities, at least it's the best you have available. You now have
Yeah.
another selection set.
So it's a sort of a benchmark question. What's the benchmark for using quantum in this particular use case? I once did a little mini poll on LinkedIn that was something like, it wasn't quantum, it was AI, but it's the same issue about explainability, which was, suppose you can go to actually use the example of an oncologist. So it was a cancer example. You've got an oncologist who's right 75% of the time, and she can explain her rationale for why she's making the judgment call that she's doing, or that why she thinks you do have cancer or you don't, or why this is the appropriate treatment. Or you could have a black box AI that, on historical data at any rate, is 95% accurate. Which one do you want to go with? Do you want to go with the human who can explain with the 75% success rate, or do you want the 95% success rate of the unexplainable
Yeah.
AI? And most people, again, completely unscientific poll, it's LinkedIn, but most people, and I think this is where I land as well, I think land with the AI, with the unexplainable black box that has a good performance record. And do we trust the quantum computer to sense cars? Let's see how it does. If it performs better than our best drivers, that's a good reason to start using it, even if we can't explain
And
it.
we better not be having our first tests on real streets.
Right.
Where did we start with? It was at college campuses for the earliest kinds of auto drive capabilities where it's limited. And we better be doing this. We better have the same kind of controls if we're going to be deploying quantum technologies in this kind of way. But as I say, best practice is that you take your quantum analysis, compare it to your classical analysis, and decide
Yeah.
what you've got. Here's the challenge, though. In a number of years from now, we won't be able to do that because the classical systems won't actually be able to do the calculation. It'll be too difficult. So we will have a situation where hopefully we've learned sufficiently about the capabilities of quantum technology that we can start to trust.
Yeah. So many more questions. Okay, so let's do two more things that I want to talk about. Then we'll wrap up. One is that I would feel delinquent if I didn't talk about cybersecurity for a second. So the big fear is that the vast majority of encryption on the internet is accomplished by what's called one-way encryption. So you take some encrypted data, you run it through your encryption algorithm, it outputs something, and it just goes one way, such that you're not supposed to be able to reverse engineer it. So you can't take some encrypted data and then run it through some reversing algorithm and come up with the unencrypted data. That would be really bad. So that said, it looks like with quantum computers, we can do that. There's this thing I know called Shor's algorithm that we
Yeah.
can run Shor's algorithm on encrypted data. And so reverse engineer the encryption and thus have the original data. That's the vast amount of encryption on the internet today.
Yeah.
It's also the encryption used by states, right? Nation states. And one of my sort of favorite things to talk about or mention in this context is steal now, decrypt later. So it's
Yeah.
not, it's not just a problem that is on our doorstep when we have quantum computers that are up and running Shor's algorithm. It's now because, let's say, China can steal state secrets now that are encrypted, in 5, 10 years from now, decrypt it, and the locations of our military bases may not have changed. And so they're going to have all this secret. So how worried should we be about this issue? Did I not accurately capture something about the problem? Where are we in solving the problem?
Yeah, you did a great job. Today's RSA 2048 is the sort of the state of the art encryption.
That's the
It's
one-way
based,
encryption.
yeah, the one-way encryption. So basically, it's based on factoring very large numbers, which is a very big challenge for today's classical computers. In fact, it can't be done. It hasn't been broken. But what Shor's algorithm proved was that if you have a fault-tolerant quantum computer, a computer that's basically almost perfect, you can actually decrypt that encryption. So here we are. We know that there's an algorithm that actually probably could decrypt, break this technology, but it's waiting for the hardware to catch up. So the question is, when will that happen? And we talked about the 10,000 logical qubits and million physical qubits. So it's a number of years away. What's happening today, however, is preparation. So you take the United States government, for example, it's told every single one of its departments they have to inventory all their sensitive data by May 2023. So they have to be able to clearly articulate where their sensitive data is. On a second level, they're going through a whole standardization process to understand how something called post-quantum cryptography. So if you have a quantum computer and I have a quantum computer, how am I protecting myself? And so they're going through that standardization process. There are two key technologies that are out there, hopefully, that are going to protect our systems. But remember, just like digital transformation, it takes time to get your systems to a point where you've got that investment and protection in place. The two types are called post-quantum cryptography, which is a way to use the software for the data that's sitting there, and then something called quantum key distribution for when the data is in movement. So you're going to need both levels of technology for protection purposes, but there are also some other types, quantum permutation pads and some others. So basically, whenever I talk to somebody, a large company, a medium-sized company, and say, they ask me when, I say, you need to start preparing right now. You need to understand the layers of protection that you're going to need for your most critical data points, applications, etc. In my world, lots of people are making those predictions about when that is going to happen. But the most challenging thing is what you described. We talk about as steal now, decrypt later, and that's happening. And so large amounts of data are just waiting for that hardware to catch up to be decrypted.
Do we have those quantum resistant encryption methods now? I feel like I've recently read about, they thought they had one, and then like some grad student cracked it in 4 hours with a laptop.
Yep. And
But
so that's happened. Two of the 6 Institute of Science and Technology candidates for encryption, Rainbow and Psych, were both successfully solved by people using laptop and not an army of programmers.
yeah,
So that made the industry very nervous. They continue to look for solutions. But what's interesting to me is I have connections with all sorts of different companies that are using their technologies for cybersecurity protection. And if any of your listeners are thinking about this, they can go to the Quantum Strategy Institute website, which is my organization. They can go to a number of other places, but really start to find those trusted vendors that they can, where you can say, show me how it works in an organization, demonstrate its capability for something you've got today, and not wait 2 to 5 years for when you see it in the media.
okay, last question, and then we'll wrap up. Talk to me a little about how accessible these computers are going to be. We all have laptops now, or desktops, or we have both. We have phones in our pockets. These computers, quantum computers, are phenomenally powerful. So one thing that people are going to raise is something like, it's tremendously powerful and 10 companies have it. That's a problem. So what is access going to look like? I know it's in the cloud. We access it via the cloud, but how many call-ins, how many requests to the single quantum computer can be made? If IBM or Microsoft or whatever reaches the million, 10,000 numbers that you're talking about, it's going to get bombarded with all sorts of requests from people who have made quantum software.
Yeah.
There's going to be a massive startup environment. How many requests can such a computer handle at once? Is it going to be something like going to be pay for play? So the big companies are going to have access to the quantum computers, whereas startups and small, medium-sized businesses forget about it.
Yeah. A lot to cover in there. If you think about who is using it, these are developers, right? So this isn't the C-suite or somebody. This is somebody who is actually coding on their desktop or laptop, and they will request through a license access to the quantum computer, and that access they'll run a project, and that takes a fraction of a second to run that project, and you get a response back very quickly. So there are 500,000 users of one type of technology called Ticket. There's 500,000 users of something called QuizKit, and these are software programs that allow you to access the quantum computers. There's a million people right there who are already accessing these quantum computers today for their very basic pilots, proof of concepts, that kind of thing. Another scenario is a company like Cleveland Clinic, where they actually install the quantum computer on their premises.
Wow.
So they believe they have sufficient hard problems in the healthcare space that they need dedicated access. That will be very unusual.
Yeah. You have to have a tremendous amount of money to pull that off.
Exactly. And so the third thing is anybody who has a Samsung new generation phone already has quantum technology. So inside the latest Samsung phone, there's a quantum random number generator chip. And what does that do? What it does is provides additional layer of security. So for example, if someone is out there trying to hack your phone, they're going to run into this random number generator chip, which creates a security field for your phone.
So interesting. So I guess it sounds like these things are so blazing fast that even if it gets millions, tens of millions of requests, each one is going to be processed in a fraction of a second. And it sounds like there won't be a bandwidth problem.
No, and what we're seeing is the escalation of breakthroughs and improvements in each one of these types of quantum computers, that capacity is not an issue. It's really about awareness. You and I talked about this before. How many people really understand what quantum or quantum computing is? And also proving out its fidelity or its capability and accuracy. So we've got a long way to go, but for any of your listeners, now is the best time to actually start investigating.
Okay, last question. There's already a rush for machine learning data scientists. There's a scramble to find them, competition for that talent. Has that begun with quantum data scientists or quantum engineers, whatever one calls them? Is that scramble already begun, or is it going to be something we're going to see in 3 to 5 years from now? Is going to be massive competition for that talent?
No, absolutely. The number one topic that's been raised at conferences in 2022. How do they find people, and not just PhDs? Yes, they're important, but we need to have people who understand science and get people who are salespeople, people who are involved in the operations environment. We need those people, and they are scarce. One of the pieces of optimism we have, though, is that we have significantly ramped up on the education and training front. So lots more courses on quantum science, quantum information science, master's programs. So we're very optimistic that those things in place will help people who are in STEM already, for example, to move into the field.
Awesome. All right, Brian. That's all the questions I have for now. You've been wonderful. This is super fascinating stuff. Thanks so much for coming on.
You're very welcome.
All right. Bye-bye.
Bye.
Thanks so much, everyone, for listening. And now let me thank the people who have made this podcast possible. So first of all, we have Delano Alexander. He's been with me since day one. He showed me even how to start recording a podcast in the first place. He does editing stuff. He's been fantastic, and he does really everything I ask him to and more. I've never met anyone else who just says so much. Yeah, I don't know how to do that, but I'll figure it out. What more could you ask for in a producer? Next up, Jennifer Strong, my podcast guru. I don't know what else to call her. She just has advised me on how to design a podcast, how to grow it, and she's responsible for, if you like, this kind of season 2 relaunch and everything around it. So thank you to you, Jennifer. Next up, Meg Marco, responsible for all the excellent artwork. Before I did the artwork, I didn't really know what I was doing. We put it together. It worked well enough, but I think Meg really did a phenomenal job bringing everything together. Garrett Lang, sound engineer that I frankly don't deserve. He's just too good for this podcast. Don't tell him I said that, though. Next up, Benjamin Koltgen. He is a professor of philosophy who has helped me source guests, identify who's interesting, who has things to say, etc., etc. So without him, I wouldn't have anyone to talk to. And then finally, Ashley Wasylenko, who helps with all manner of administrative things, making sure that the podcast guests find their way to the podcast, can schedule the recording, get their bios and headshots, and really just keeping the show on the rails and me organized. Thanks to all of you. Really appreciate all your hard work.